At 5:36 p.m. on March 27, 1964, an earthquake rocked the state of Alaska. It could have happened anywhere, at any time. What caused it? Why was it so devastating? How can we learn to cope with earthquake hazards? For decades, man has looked in the wreckage for answers. Bit by bit, after each earthquake, man has tried to piece together the puzzle in an effort to recognize earthquakes for what they are. The task has not been easy, but with each catastrophe, geologists have learned a little more. Earthquakes can happen anywhere. The zones in which they are most likely to occur now have been identified, but the exact time and place cannot as yet be predicted. Most earthquakes occur where there are ancient wounds in the earth, along faults breaking the crust, and are caused by the forces that build mountains. Some earthquakes are related to volcanic action, but many earthquakes occur in regions not associated with volcanoes. Approximately 700 of the shocks recorded each year may be classed as strong, capable of causing considerable damage in the areas where they occur. It has been estimated that more than 1 million earthquakes occur throughout the world annually. They range from minor temblors that are barely perceptible locally to catastrophic shocks. The greatest quake-producing zone, known as the Circum-Pacific Belt, runs completely around the Pacific Ocean. 80% of all shocks recorded occur in the Circum-Pacific Belt. This unstable area is also called the Ring of Fire, because most of the Earth's volcanoes occur in the same zone. During the past 200 years, over 1,000 strong earthquakes have been recorded in Alaska. 14 have been catastrophic. Geologists believe that the state is plagued with earthquakes because of its many active faults. 3 principal faults are the Fairweather, the Castle Mountain Lake Clark, and the Denali faults. The friction of the rocks on each side of a fault normally prevents slipping of the earth. But since stress is continuous, strain builds up. When this strain passes a critical point, a point of no return, the friction on the fault plane is overcome. The rocks along the fault snap past each other, releasing as much energy as thousands of atomic explosions. Shock waves moving through the earth at thousands of miles an hour shake the land. The intensity of damage is related to the distance from the epicenter, the point where the first movements appear to start, and the geologic environment. Clay, sand, and gravel, for example, respond more intensely than hard rock. The epicenter of the March 27th earthquake was located about 80 miles from Anchorage in a region of high, rugged mountains. The earthquake produced significant damage to structures and property over a land area of 50,000 square miles. Ice was cracked or buckled on lakes in an area of 100,000 square miles. The quake was recorded throughout the world. Here is how it looked on a U.S. Geological Survey seismograph located at the Hawaiian Volcano Observatory on the island of Hawaii. With the aid of seismic records, eyewitness accounts, on-the-spot examination and photo coverage of every type. Let's see what geologists were able to piece together of the earthquake puzzle. To begin with, uplift and subsidence accompanying the Alaskan earthquake affected an area of at least 34,000 square miles in south-central Alaska. The major subsidence area included the Kenai Peninsula and the northern two-thirds of Kodiak Island. The major area of uplift included the islands and mainland of Prince William Sound. Extensive tracts of mudflats, beaches, and reefs formerly below tide level are now exposed. In many areas, because there were no accurate pre-quake measurements of elevation, the changes had to be reconstructed from evidence such as barnacle lines, which marked the former high tide level. This dock, for example, was raised far above high tide level. What were the major effects at population centers such as Anchorage? The damage, estimated at more than $200 million. It was caused both by seismic shock and by landslides triggered by the quake. This is what happened in downtown Anchorage. The geologists found that earthquake vibrations themselves caused less heavy damage than the vibration-induced sliding and settling of weak deposits beneath the city. From the chaotic jumble of wreckage, geological survey teams pieced together what happened at Turnagain Heights. Meticulous examination and mapping of exposed details within the destroyed area, combined with extensive subsurface sampling, turned up vital information. From the evidence collected, scale model experiments were designed in the laboratory of the University of California at Berkeley to determine how these materials behave under simulated earthquake conditions. Using the same ground materials found at Turnagain Heights, investigators recreated the Turnagain slide. Experiments like this helped substantiate reports from the field that the landslide occurred when seismic vibrations drastically reduced the strength of the clay, which failed below sea level, and caused the ground above to break into blocks and move seaward. More than a dozen landslides occurred in Anchorage. Most of the damage and casualties in the downtown area were caused by the L Street and the 4th Avenue slides. Both landslides were lateral movements of relatively coherent blocks, gliding on unstable deposits similar to those that failed at Turnagain Heights. In contrast to Anchorage, geologists discovered that the city of Whittier, which is built on bedrock, experienced little damage from the shock, even though it was 40 miles closer to the epicenter of the earthquake than Anchorage. Whittier was, however, seriously damaged by sea waves. Elsewhere in Alaska, violent ground motion triggered thousands of snow avalanches and rock slides. Many of these blocked or threatened the Alaska Railroad and the highway system. Numerous ground cracks, areas of subsidence, and mud spouts occurred throughout the zone of damage. Glacier ice broke into huge precipices throughout much of central Alaska. The city of Valdez, located at the head of a deep, steep-sided fjord, was completely crippled by a sudden submarine landslide. This once active port was destroyed when a block of ground 1,200 feet wide sank into the sea. A seaman aboard the steamship China filmed Valdez Harbor during the earthquake. Seawater poured over the slide escarpment. The cannery slid into the sea. 30 people lost their lives as the town dock pitched into the bay. This is all that remained on the waterfront when it was over. Ground cracks opened throughout the town. Plots of these cracks showed that the entire town lies on incipient landslide blocks. That could wipe out the community the next time the city is shaken. Consequently, a search for a more stable site was undertaken by the United States Geological Survey. The city voted to move the entire town to a safer locality 4 miles away. Construction began immediately. Submarine landslides triggered by the quake generated huge sea waves. In Valdez Passage, one of these waves deposited debris 220 feet above sea level and destroyed the navigation light. Waves breaking over the land sheared off trees 100 feet above the beach. At the Indian village of Chiniga, a wall of water 90 feet high swept away all but the school and one house. The height and force of the waves generated by submarine landslides were matched by a second type, seismic sea waves. Born of the uplift and down warp of the sea floor, enormous seismic sea waves called tsunami traveled at speeds in excess of 400 miles an hour in the open ocean and struck with destructive force all along the coast of Alaska and the west coast of North America. The tsunami lashed at Crescent City, California. Kodiak was pounded unmercifully by the tsunami. Residents had to be evacuated. Waves crested 30 feet above the normal highest tides and left watermarks to prove it. The town of Seward was one of Alaska's busiest ports before 4,000 feet of its waterfront slid into Resurrection Bay. The Alaska Railroad docks were demolished. Box cars and locomotives were tossed around like toys. The newly formed shoreline consists of the same unstable materials as the old. The ground behind it contains many tension cracks. Future submarine landslides may occur. The Alaska Railroad was extensively damaged. Rails buckled and tracks dropped into the sea. The damage caused by seismic shock and by landslides. Railroad and highway bridges were damaged severely. Investigations revealed that both horizontal and vertical displacement of piles took place. Also, piers and piles were sheared by ground movements. Lateral spreading of the ground near stream channels caused tracks to separate, shearing the bolts. Field surveys highlighted one significant point. The reaction of different subsurface materials controlled fracturing, compaction, lurching, and landsliding more significantly than distance from the epicenter. Geologists discovered that structures built on bedrock were damaged less than those erected on unconsolidated deposits. Survey reports emphasize hazards along shores made up of unconsolidated deposits because of the extreme susceptibility to sliding. There also, land level changes have the most disastrous effects, spawning sea waves, disrupting navigation. Though man has learned much from the wreckage and destruction, he needs to know much more. From the debris, he has gathered valuable information on how better to cope with an earthquake. But the acquisition of this knowledge is not enough. It must be put to use now. Your federal government is extremely concerned. It believes the earthquake knowledge gained to date must be applied to land use, not only in Alaska, but everywhere earthquakes are prone to occur. One should not demand builders to over-engineer against dangers because the dangers have not been adequately evaluated. But it is gross negligence to endanger lives for lack of scientific and engineering knowledge of geologic hazards. Building codes must be improved to take into consideration earthquake design criteria and then adhered to. The loss of over 100 lives and $400 million worth of property damage resulting from the Alaskan earthquake occurred in a sparsely populated area with approximately 1 inhabitant per square mile. What is to be the fate of our earthquake-prone urban areas, such as these, along California's San Andreas Fault, with several thousand inhabitants per square mile? Unless we recognize and design for the geologic potential of the land on which we build, work, and live. As more is learned about the sudden release of stress in the Earth's crust and its effects, the United States Geological Survey will continue to provide additional pieces in the earthquake puzzle.